Hello again. This is the third lecture on internal flow for ME 544. What we're going to cover today for the next 7 or 8 minutes is how to handle problems where we don't know the surface temperature of the pipe, but we know the temperature out for an external airflow or a fluid flow around the pipe flow. So what we're going to do then is write our equations in terms of T infinity, the external flow temperature, and obtain relations for the change in temperature of the flow as it goes from the inlet to the outlet of the pipe. So we start with drawing a temperature versus distance along the pipe diagram, and then our hypothetical temperature curve is drawn. And again, as we did before, we will write relations for the temperature difference between the temperature at infinity, the inlet temperature, the temperature of the outlet, and the temperature of infinity. So how do we start with the analysis? Well, because we now have a situation with an external flow, we go to a resistance network, and we then will have to compute the internal and the external heat transfer coefficients. And we will cover that in just a bit. If we have those, we can then construct an overall conductance and then use that plus a revised form of the log mean temperature difference to compute the heat transfer and the temperature differences. So if you forget how to do this, just review your notes on resistance networks, where the resistance is really 1 over the conductance. So let's go ahead and look at an example. And this example is very, very similar to the, I think it's the first homework problem that's due next Friday. We have a thin walled tube, so we don't really worry about the conduction across the tube. 10 millimeters in diameter, 20 meters long. It has water entering at 27 degrees C at a flow rate of 0.2 kilograms per second. And it's heated by hot air, 100 degrees C, flowing over the tube. 2 questions. What is the outlet temperature of the water? And what's the heat transfer from the air to the water? So again, with these type of problems, always draw a temperature versus length diagram. Label your air temperature at infinity, your incoming temperature, and then the unknown outlet temperature. And this will then be the heat transfer. Now, one particular sort of complication for these types of problems is knowing what temperature to use when you get the fluid properties. And what I've done here is show what I usually do. I just make guesses, and hopefully the guesses are close enough to the actual answer. If you're being paid to solve a problem, you need to iterate to probably tighten up your answers. So we will need to know the pipe surface temperature, and I'll just go ahead and assume it's halfway in between the outside air and the incoming water temperature, which is then 63 degrees Celsius. And then, armed with that, I can then look at the film temperature around the cylinder. So that would be 100 plus 63 over 2. That'd be about 82 C or about 350 K. I like to just pick numbers where I can go to the tables and not have to interpolate. On the inside, what we'll do is make an assumption that the temperature rise of the water is low enough so that we'll just look at the properties at 27 C or 300 K. Then going to the tables, we'll pull out the relevant properties we need: viscosity, Prandtl number, thermal conductivity, and on the water side, the viscosity, Prandtl number, thermal conductivity, and specific heat. Then, as we've done before, we calculate our Reynolds number and our Nusselt number. Let's just cover this one up so we can focus on the inside flow. When you're given flow rate and you need to calculate a Reynolds number, this is a good relationship to use that you get using the continuity equation. So when we put the numbers in, the Reynolds number turns out to be about 30,000. The critical Reynolds number is 2,300, so it's highly turbulent. And again, since it's a very, very long pipe, the length over diameter is greater than 10, it's also well developed. If you then go to the correlations for turbulent cylinder flow and put in your Reynolds Prandtl number, again, for water, it's always around 5. And then you'll find Nusselt will be 176. Armed with that, you can then compute your inside heat transfer coefficient, which turns out to be around 11,000. And then now we look at the inside, looking at the air and flowing around the pipe, compute its Reynolds number, and it turns out to be about 5,000. And then you need to go to the cylinder tables in that handout to find the coefficients A and B for the Nusselt, Reynolds, Prandtl analysis. When you do that, you'll find the Nusselt number is 32, and that means that the outside heat transfer coefficient will be about 100. Now, look at the difference between the two. Inside, it's 10,000 or more, and outside, it's around 100. So the largest resistance, of course, is on the air side, which means when we compute the overall conductance, it really won't be much different than 96. And sure enough, when we do that, it comes out to be at 95.7. Hasn't changed much at all. So now we can finish the problem, and we'll go first calculate our temperature differences. And again, knowing our exponential curve, and now knowing our conductance coefficient, we can then compute that exponential term, which is 0.93. We now solve for the temperature of the fluid leaving the pipe, and it turns out to be 32 C. That's only a 5-degree temperature change. So the assumption we made that the mean temperature really doesn't change much for properties is it's okay, not too sleazy. And then finally, to get the overall heat transfer, UA delta T log mean, we compute the delta T log mean. Again, we calculate, now that we know the temperature differences in and out, we can compute the delta T log mean at around 70 degrees. We drop that into our Newton equation. Now knowing U is about 96, and the delta T log mean is about 70, put in the pipe geometry, we get about 4 kilowatts. So I think this is a standard type of problem. You'll have some homework problems like this. So good luck, and see you with the next talk. Bye.